Okay, so this is the picture we were looking at last time at the very end, and this is a big construction that I think captures a lot about what we care about. It is the how to represent a plane in the three-dimensional space and the meaning of all those numbers. So we have discovered the plane, the formula for the plane through what? Through how that plane crosses the coordinate planes. So the blue plane crosses the three coordinate planes, and the normal situation is, generic situation of two planes is that they intersect by a line. Okay, and so though we produced two lines, which is sufficient, as we could have produced three, right? That line at the bottom is also counts, but we produced only two, and that was sufficient for us to figure out the plane. So remember this, right? So once again, we crossed it on the XZ plane, that is at the top, and the violet, I suppose, a violet line on at the bottom, a YZ plane. And so, in other words, remember where we're coming from. So far, these planes, these axes, are not all equal because of our interpretation of that plane. We are so far looking at the plane as the graph of a function of two variables. Or better yet, I encourage you to start thinking about this function less than a function of two variables, but more as a function of one vector variable. So as you can see, the input, the whole xy plane is made of inputs, and those inputs are points or vectors on that plane, and the output is z. So x and y on one side and z on the other side, and they do not really you should not be mixed up. Same applies to lines, by the way. So as you can see, we chose then to look at those two planes, both of which had z-axis there. So xz and yz. So we paired up one of the two independent variables, x and y, on the horizontal axis, and the vertical axis the same z-axis. Okay, so it is like a partial representation of our function. So it depends on x and y. What happens if what has happened is if we allow x to vary still, but we set y equal to 0. So see over there I wrote here y equal to 0. So that's the xz plane. It is where y is equal to 0. And then everything certainly simplifies, and we are dropping back to calculus 1, one-dimensional situation. And so that's why, by simply looking at that line, we were able to figure out what that line is. So intercept, y-intercept 3, slope -3/2. And then we did the same. So two independent variables. Now I did the same with the other variable, which is y. And once again, y-intercept 3, slope -3/4, and that is my equation. Equation limiting our function, a big function. We're limiting it to the case when x equal to 0. Okay, so that doesn't seem like, if you think about how little we have captured from our plane of our function of two variables, very little. So that whole huge plane, infinite in all directions, we only took two lines like this. So the violet and the green lines like this plane, two lines. That's all we got. It might seem very little, but because of the plane, of the nature of the plane, it's very predictable. It's repetitive. So as I indicate over there, we are not getting just one line, but a bunch of lines. All of these lines are pretty much the same. Okay, so we could have cut with a different kind of planes, producing very similar story. So instead of x equals y equals 0, I could pick y equals 0. I pick y equal 1. Okay, and then I'm getting this line. Then I pick y equal 2, and I'm getting this line. And so on, I will get a bunch of lines, and they're all here. And they will have all the same slope, only the y-intercept will vary. Z-intercept, technically. And I do the same with the other line, this one. So here x equal to 0, and that is my line. But I could also pick x equal 1, and that will be my line. X equal 2, this will be my line. So it is sufficient for us to what we've got, and that justifies why we didn't have to do any extra work, and just to merge together this information. Z is a function of x, and z is a function of y, as if it was a function of one variable, or rather two functions of one variable, and we merge them into one, as you can see over there. Okay, that equation at the top. Okay, so if we look at it and we remember where these numbers came from, we know what it is. So well, let me write it out. So suppose I have my function z equal mx plus ny plus something else, p. Okay, so I can identify now these three parameters, m, n, and p, based on my interpretation. So what's the meaning of p? What? No, p, the last one. Z-intercept, yes. Z-intercept. So it is where the my plane crosses the z-axis. So literally the intersection of our plane with the z-axis, right? So once again, this is the picture. So this is what I'm talking about right here, or this one, this point I'm talking about. Okay, and then indeed, though, the other two numbers will be slopes with respect to x and with respect to y. So slopes with respect to x and y, respectively. So whichever you cross with, to get the slope with respect to x, you cross with a plane parallel to the y, parallel with a plane parallel to not the x-axis. Well, x-axis is an axis, so we cannot really speak of planes parallel to the x-axis in that sense, but rather what is it parallel to? To get the slope with respect to x, I cross with, look at it, -3/2. I cross with what kind of plane? I'm crossing with these planes. No, wait a minute. Yes. So xz plane. Parallel to xz plane and respectively yz plane. Yz plane. Okay, so let's see. Well, there is a more general way of representing this. So you can think of this equation as, how should I put it, the point slope form. No, this is z-intercept slope form. That's what it is. So remember, I'm trying to refer back to one-dimensional situation, and we had two ways to represent lines. The main ones: slope y-intercept, in the point slope form. Okay, so this is this refers to z-intercept slopes form, if you like. So once again, three numbers, z-intercept and two slopes. Gives me this form. Okay, so P is the z-intercept, the M and N's are the slopes, and we have the equation. Okay, so it's analog, once again, what I'm referring to, analog to y equal mx plus b, right? Where m is the slope and b is the y-intercept, right? I put it in the same exact order. And if you drop out of either this drop out, it will be exactly like that, or I drop the first term, once again, it will be exactly like that. Okay, the other one was the point slope form. So remember the point slope form. What's the point slope form? A one-dimensional story from calculus, from pre-calculus. Y minus, say, what? Anybody remembers?
Equals to something.
Y minus, say, b is equal to mx minus a. So it passes through the point AB, and it still has the slope m. Naturally, the slope is still the same. No matter how you put it, the slope will appear in the exact same way. So, then the y-intercept story is also a point. It's just a very special point, in that's why the that first form over here is not general enough for our purposes, because you have to refer to the z-axis specifically. And fortunately, there is the other form, the point slope form, when we concentrate on an arbitrary point. Any point AB that's picked on the line will give me that representation. Okay, so I will have a similar form for the plane. So first of all, look again at this formula. That it's certainly on the right. Important to understand the meaning of everything here. Remember that. Well, you can write it this way. That's where the information is hidden. Is that m is equal to y minus b over x minus a, which is important. Why is it important? This form. The slope is y minus b over x minus a. What's the meaning of the fraction? It is why. That's why it is. It is why it matters. That you actually, the idea that the slope is rise over the run, you can actually see it in this algebraic representation. And it works out especially nicely because it's not just any two points. Any pair of points, A, B on one hand and X, Y on the other, will have the same effect, the same slope. So naturally, we know what we know about straight lines. They have the same slope everywhere. So that is in particular what we're seeing here. No matter what X and Y are, that point x, y on the line, you keep moving it along the line, it will still produce the same slope. Okay, so we are not in such an easy position anymore. So that last convenient equation we'll have to forgo that. But the rest will be very similar. You can probably guess what the equation will look like. So suppose the plane passes through the point ABC, and same slopes once again m and n. So what would you think the equation should look like? Z minus C equal mx minus a plus n y minus v. That's right. Okay, so as you can see, we're by moving c in the left hand side, we sort of abandon, or at least step away a little bit from the idea that we're talking about the function, but it's still there, right? So you can still express z in terms of everything and have it written explicitly. But here this form is especially nice, and that is, but there is a certain degree of challenge to recognize something extremely important here. I say that this expression on the right is familiar. Multiplication. You see multiplication, right? And you see addition.
You just carried that e to the other side.
What?
You just add that e to the other side and you got pretty much the same one.
No. I just want you to look at what's on the in the right-hand side. So as I said, so the hint is multiplication followed by addition. What? It is. This is the dot product. This is indeed the dot product, and that is a very important observation because it will allow us to utilize our vector algebra to such a degree that that kind of a thing that doesn't look complicated yet, but once you go to high dimensions, that will certainly explode if you try to move to the next dimension. But even in lower dimension, you still can utilize dot product to make everything compact and manageable, and all our understanding of algebra of vectors will come into play, and you can deal with angles and distances and everything. So dot product of what?
That'd be like the last one,
So what's the first vector? Remember, the multiplication is coordinate-wise, and we are these two terms. One corresponds to x, the other corresponds to y. So it aligned perfectly as intended by the dot product. So the first vector is mn. So x of that vector, m is the x component, n is the y component. Similarly, what's left is x minus a, y minus b. That's the second vector. So so far it doesn't look that simple, but we can take it one step further, and so that's what it is. What can I do with the second vector? What?
you break it into two.
Yeah, I could break it into two indeed. So I have mn, and notice how things are aligned already, rather than based on the coordinate-wise treatment. That's we are moving from coordinate-wise treatment to sort of content-based treatment. So, for example, I have the first vector. It contains both of the slopes, rather than have thinking about x here and have slopes, y-intercept, everything there, and then do the same with y. That's difficult because then you have your x and then y. What if I have one more variables? That's not working out. Combine similar things together. So I combine in the first vector, I combine both of the slopes. Okay, so if I go to the next dimension, there will be three slopes there. And the second vector, once again, I break it apart, and what I have here is my x variable, not my x variable, my independent variable of my function of two variables is right here. And I subtract AB, which is the point. the point. So remember, point slope form. So what the point we're referring to, this is it. This is the point. So remember, it is, right here. So it passes through point ABC, point ABC in the XY plane. In the XYZ space. But if we look only what's happening on the XY plane, then this is what we are observing. So that is the point, and this is the variable. And these are the slopes. In a way, you can say that that vector is the slope, is a vector-valued slope, if you like. So two slopes combined together give you a vector slope, which contains conveniently contains the information about both directions, along x and along y. So if you have that in your pocket, you can go either one direction or the other, and you'll know the slope. Okay, so because you are on the plane, you have at least two directions to follow, and then you need both of the slopes. In fact, as we're going to discover, it doesn't matter which way you go, even all the infinitely many directions between x and y, they are still available. You will be discovering the slope in a similar way. I think I have another picture here which illustrates, slightly differently. So it's the same pretty much story, except we are looking at the slopes more carefully here. So 0.241, and then what if we start? I guess the point is, what if we start with point P to begin with, and then we are supplied with two slopes, M and N. How do I get the plane? We went in the opposite direction yesterday, or last time. So what's happening, look at it. So I started with point P, and then just like I was building a line in the one-dimensional case, I draw a line with that slope. So as you can see over there, on the left, on the top right, I'm going in the x direction, and the slope is -1, so that's why it's going down like this, right? Okay, and then I do the same with y over there. So I'm going from point P along the y-axis, and I'm dropping down by 2. The slope is steep, -2. Okay, so then these are the two lines. Literally, those two lines that we drew, they define the plane, and that plane you see on the right. Okay, and then as I mentioned before, you will be able to discover slopes, all the rest of the slopes. So for example, if I go in this direction, like this, I will still be able to determine what the slope is from those two slopes. How? The answer is always the same. It is the dot product. The dot product will tell us what that slope is as well, so later on. Okay, so back to this algebra. So this is still somewhat incomplete. In fact, it is incomplete primarily because it is still two-dimensional, and so let me. Yeah, it is. I'm afraid it's just two-dimensional, and it is not going to do the trick. Well, but it gives us the idea of what is supposed to happen here, in which direction to progress. So at this point, I could certainly try to make a case for vector representation of this line, which is still not entirely perfect, but let's say this vector, I call it n x minus a. Okay, so that's what we're looking at. If you are looking for vector notation, then that's what you're facing. The vector of slopes, dot product with x, the variable, minus a, the location. So if we are still on the xy plane, so this is my a. It is, what is a? It is the point on the xy plane that we chose it to be like a reference point. Okay, and then I compare to the value of another reference point by the rather the variable now, which runs throughout the whole xy plane, is the point x, and then I do the difference of these. So this is my x minus a. Okay, and then what I'm saying, and then the operation that I carry out with a vector n, which is also fixed. So the red dot a, the red point a, is fixed, so as a parameter of our line. And then there is also a vector n, say maybe like this. Vector n also is given the vector of the two slopes. Okay, so then the right hand side is I multiply this vector x minus a, I multiply by the vector n. Okay, so it is just a way to rewrite the original equation, the original right-hand side in our equation over there, in a more compact and vector form. And it suggests that once you reach the vector form, you realize that it is probably can be done, not probably, definitely can be done in any dimension. So you can imagine that you're talking about some kind of a hyperplane in n-dimensional space. Why I'm saying hyperplane, because of the question is what is the usually when you say plane, it is the plane of the two-dimensional. Look at it. It has two variables x and y. But imagine if we're talking about the linear function of n variables, then the whole procedure works out exactly the same way, right? So except there would be more terms. So I would have more terms here. So if I have n variables, I will have n terms. And there will be n slopes. And there will be n coordinates to this point. So this point will have n coordinates. X capital will have n coordinate as well. Okay, so that is how you build a linear function of n variables. So that will be then this will be long, very long n terms, but the last line will be exactly the same. Okay, so it's still dot product of a certain vector times some other vector which indicates our step. Okay, so the question is then if we step away from from A, if our new location is x, our step is x minus a, so like a displacement. And then we do the dot product with the vector of slopes n, and then that indicates how far z changes from its reference point. Its reference point is c. Okay, so our deviation of so this is the change of the input, right? So a is the reference point, and we change from a to x. So then the change is x minus a. Okay, and then this is the change of output. Okay, so and as you can see, what we're saying here is that the dependence of the latter on the former is linear. Right? Change of the input, dot product with n, gives me the change of the output. Okay? So that is how we understand linearity in higher dimensions. So linearity in one dimension is simple multiplication by a number. Once you get to functions of several variables, that linearity takes a different form. It is still multiplication, but you have to multiply by a vector this time, because if I have n increments, different increments, how do I put them together into one number? And the answer is dot product. Okay. So before we proceed to a more general view of this, let me examine the. Let me go back to straight lines. It's very easy to confuse the two. They are really, really different. Lines, planes. Look, very different, but some of the language is somewhat similar. We even had two slopes, remember? We had a line had two slopes with respect to x and with respect to y. So I want to do a numerical thing in order to demonstrate well the difference. Okay, so this is what we did a couple of days ago, last week. That's a line. Okay, so that's a line. And I did it in 3 dimensions. So let me scale back to dimension 1, which is simply, I'll just delete this. I delete this, and I delete that. Okay, so we only have one to worry about. Okay, so this is a straight line. The straight line that we are seeing, it is on the xy plane. The variable t is suppressed. Okay, the variable, the independent variable, input variable t is not shown. So if I highlight this, you can see where the data is coming from. It's coming from x and y. Okay, so you can speak of, however, now the angle that I want to look at is actually how I see the function as a function. So I have two functions here. If this will be, in either case, this will be my input, and then x is the output or y is the output. So here's one function. This is the input, and this is the output. Okay, let me plot it. This. Okay, so this is how x depends on y. X depends on t. I'm sorry, on t. X depends on t. Okay. So once again, I highlight C, dependence of x on t. Then I can do the same with y. Right. So this is going to be y depends on t. If I just do this, okay, and I change this, so it is y depends on t. As you can see, the whole thing is happening in 3-dimensional space. So with 3 x's, 3 coordinate planes. And these 3 coordinate planes are now visible here. The projection of my line that Excel is incapable of plotting has 3 projections or shadows on those 3 coordinate planes, and that's what we are seeing them here. Okay, I could certainly, to make that point clear, how about I put here, say, -2. Okay, so they all not all look the same. So these are actually 2 functions at the bottom. X depends on t and y depends on t. And as x and y are related to each other as 2 dependent variables, is at the top, on top right. Okay? Okay. So and there is nothing else. And the line, we are looking at the line in 3-dimensional space. So it does appear that if I look at these two, there are 2 slopes, and they are actually given here. So my direction vector is -2, 3, and -2 gives me the slope of the first line, and 3 gives me the slope of the second line. If you feel that there is too much overlap of the same terminology as with planes, that is true, and that's unfortunate. So that's why I actually want to confront it now and go back to lines, so that there would be no confusion. The difference is these are projection shadows of our line. In the meantime, in the meantime, those two numbers, also the slopes, they are not projections of the plane. They are intersections of the plane with the planes. So in either case, we produce lines, two lines, but the difference is that how we made them. Intersection or projection. How do you make a line from a line? Well, your projection would work. How do you make a line from a plane? You cannot project, you intersect. Okay, and that's why we still were able to do it. Plane with plane intersect, and it gives me, as you can see, a line. Okay, and then naturally, when you put these together, that's what you end up with when it is a plane, and that's what you end up with when you have a line. I still want to. So where's my line? Here's my line. I still want to. What I want to do is now I want to actually build, also use Excel and build a function of two variables. So you can see the difference, because these formulas are sometimes just not, they're just so compact. Algebra sometimes works against you because everything seems so tiny and easy and compact. But what about data? This is the data that produces the line, one line in space, as well as three as a visualization. This is just visualization. They produce the visualization of the projection of the three projection of the line of the three planes. Those same three planes as I see here, right? Those three planes over there. So this is my line. I don't know. This is my line, right? And then I have three projections like this. Okay. So that's with the lines. Let's use Excel to do what? To construct this or similar plane. Okay? Well, with your help, we'll see how you understand functions of several variables. Okay? So I wanna collect data for my function of two variables. Okay, so remember what the input should be. So for the line, the input was a column. And here, what should be the input? So once again, look at this as a function of one variable. The input excuse me, is a column. Function of two variables. What's the answer? And the answer is not two columns now. What?
What are we trying to make?
We're trying to plot the graph of a plane, of a linear function of two variables. Okay, so what should be my data before we're actually plotting a function? Where is my data should be located? I am referring you to this picture. So what should be the input?
Coordinates.
Yeah, two of them.
X, Y.
Right. Okay, but how many? So for example, over here I had what did I have? I had 20. How many points did I have? I have 40 points. How many points should I have?
So would 40 still be okay?
What?
Wouldn't 40 still be okay if you had?
No. I wanna match them up. So I have 40 for X and 40 for Y. So
80
80.
or 160?
40 for X and 40 for Y. How many is it? Think about it. What?
Is it 160?
Yes, it is.
Yeah, because you got
What?
two of them. You got two X's and two Y's. So if both
No.
40, 40, 40, 40, then you got 160.
No. I didn't understand. You didn't. No, that's not the right answer.
Oh.
40 and 40. 40 X's. 40 X's, 40 Y's. Adds up to what?
80.
No.
What?
Let me.
Just 40?
Hold on.
40 X's, 40 Y's. It's a trick question, but
40 points.
what? No. Let me show you. 40.
No,
These are
20.
x's.
It's
These are
20.
40. These are x's. These are y's. 40 and 40. How many? How many?
Is it?
40 and 40. How many?
It's a 40.
No.
Is it 20?
160?
No.
It's an 80.
There's not 80 in there. Okay, so we're talking about a plane.
I'm talking about a square.
So there's 160.
Oh, so because it's one down.
No, you-
It's one. It's like.
It's not 160. Close, but not 160.
It was 40 squared.
160.
That's right, which is not
Which
160.
is 1,600. Right?
That's right.
Okay. There you go.
The answer is 1600.
40.
So with the same accuracy, x and y, x is an independent variable and y is an independent variable. Not only they're independent of each other, so they vary independently, which means that, yeah, you gotta need the whole square. Yeah,
Why do you do square?
because it is a square. X's and y's, they form a square and they vary independently. So you need every single point within the square you're gonna need as an entry, as an input.
You're saying in that like one picture in the like notes you took, that's like the pink part of that, like that's.
Over here, yes, the pink part, it is indeed every single point we'll have to take into account.
Okay.
Because, well, think about it. How else do you end up with a plane? It's like think about any function of two variables. Well, I mean, think about coordinates. So if you have your coordinates, you're talking about a map, and you say building a map, an altitude. Okay, so for every location on the map, you need to know the altitude. So every combination of two coordinates will have to be taken into account, and you're gonna go like this to cover the whole square on your map in order to have an altitude at each location. Okay, so so in other words, I'm gonna over here, I'm gonna have the x-axis at the top still, y-axis at the vertical on the left, and then all my inputs will be a square. So let's do that. Okay, so I'm gonna put x's here. So let's start with 0. 0. Let's make it easy, equal to previous plus 1. Okay. I'm not gonna do 40. Shoot. I'm gonna do just 20. Should be enough. Okay, so these are my x's, and y's will go vertically. So x is to the right, y's to the bottom. Okay, so once again I start with 0, and then I progress one at a time. Okay, plus 1. Okay, so these are my these are my y's. Okay, x's and y are taken care of, but every single entry within this area will have to be, for each of them, we'll have to compute the value of z. Right? So now let's have a formula. Let me take pretty much the same formula. How about negative 2x? Let me do it carefully. References are a little bit tricky here with Excel, so it will be row 2, same column. Row 2, same column. Okay, plus, or rather minus 3 multiplied by y, which is same row, first column, C1, and say plus 3. Okay, so the formula is negative 2x minus 3y plus 3. Okay, so now I'm spreading it out. So I am computing then within this square, I am computing all the values of z. So these are the z's in this square. Okay? Okay? All right, so, and now what remains is just to find, I do believe that there is a chart that will take care of it. I just need to find it. Where is it? Uh, they move stuff around excessively. Now I don't see where the right chart is. Oh, here it is. Okay, so a little looks a bit awkward, but fortunately you can rotate it to see that plane that we have built. Okay, so it is indeed a plane. We did not skip any of the entries. In the middle. Imagine that some of the entries in my rectangle are missing. It's not going to be would not be a plane. If I only took one row, I would end up with a straight line instead of a plane. If I took one column, once again only a straight line. It is the data itself, the input data is two-dimensional. It is a rectangle, and that rectangle is pretty much being lifted, creating that plane. If you look carefully, you can probably, can you see the slopes? Those two slopes that we talked about? I guess the way to do it is to rotate it in such a way that our plane would, well, yeah, so we will look at the intersections with the coordinate planes. So the one that is behind this one, this is the line that we care about, right? This one, this line. Do you see what its slope is? Unfortunately, the numbers are not clearly provided, but roughly horizontally it's roughly 20, and vertically we drop by. And vertically we drop by what? So once again, that line at the back, that line, it is horizontally we progress by about 20, and we dropped by roughly 60. Yes, not 60, but rather maybe 60. Yeah. So 20 and 60, which gives me slope -3, right? Remember that was the formula. That is the y slope with respect to y, -3. Okay. So all right, I'll assign homework later today.